The recording seems to have cut out here, and hopefully it was just at the very end. But it's not a big deal. All I was kind of showing is that this result is kind of universal. This isn't a result about ammonia levels. This is a result about normally distributed data. What's the probability that the random variable has a value between minus 1.5 standard deviations and plus 1.5 standard deviations of the mean, and it doesn't matter what it is. So for example, if you're looking at heights that we're supposing are normally distributed with an mean average of 175 centimeters, standard deviation of 15, this is the mean minus 1.5 standard deviations, this is the mean plus 1.5 standard deviations, you're still going to get the same answer. Okay, so I'll move on to this next question here. So the lengths of pipes are assumed to be normally distributed with a mean value of 5. So this is a kind of equality situation. These pipes are supposed to be 5 meters, and in fairness, the standard deviation is only 3 millimeters. So most of them, really, 2/3 of them, are within 3 millimeters of 5 meters. So the equality in these pipes is quite large. If that was kind of like 3 centimeters, you're going to get issues for people using the pipes in types of construction, etc. Okay, so the question is, what percentage of pipes, and that's the same as the probability of the randomly selected pipe, what percentage of pipes have a length less than 5.002 and within 1 centimeter? So this is about how many of them are not excessively long, and then this is which one they're kind of within a centimeter of being correct. So if someone slaps on 5 meters as the length of the pipe, they're going to have some statistics backing that up, and they might have some ISO whatever standard on them, and maybe it's that 99.9% of them are within 1 centimeter or 5 meters, something like that. Okay, so we're going to say let x be the length of the pipe, and it's normally distributed. That's assumed. The mean is 5, standard deviation of 0.003. So in the first question, we're looking for the probability that the length is less than 5.002. So we'll write this in notation and draw a picture. So we're looking for the probability that the length of a pipe is less than or equal to 5.002. And as we explained, it doesn't matter if you include the equals or not, it doesn't make any difference. So this will be an area. So what we should do is draw, and actually I can kind of exaggerate this drawing if I include. Well, I won't. So if you're actually to draw this to scale, it's going to be a very, very narrow peak, because the average is 5 and most of it is within 3 millimeters. So I won't draw that though, but that's what it would look like if we drew it to scale. I'll exaggerate it, just makes it easier to actually do the question. So here is the 5, the dominant average. Here's x, and we're looking at 5.002. And we're looking at the probability, what's the percentage of pipes that have a length less than that. So we're looking at the long left tail of 5.002. So straight away we can see that 0.002 is 2/3 of the standard deviation. Or maybe we don't see it. And if we don't see it, we use the formula. So we wish to find this area. We're going to translate it to a question about the Z distribution. So let's do that on the next page. So this is the same as the probability that Z is less than Z1, where we can find Z1 using our little formula. So Z1 is the X value in question, which is 5.002, minus the mu in question, the average, which is 5.00, or 5, I suppose, divided by the standard deviation, which is 0.003. If you bang that into the calculator, you will get 2/3, and now this is a Z value. We can only go to 2 decimal places, so we should round this to 0.067. And therefore, if we're going to draw a picture, the answer is the area. So let's draw our Z curve. So basically we're going to draw a version of this picture, but instead of the mean 5 and this, we're going to have 0 and 0.067. So this always goes to 0, the peak, and then this, well, it depends on your formula. This formula here is the Z is equal to x minus mu divided by sigma. Okay, so this is our z picture. This is the 0. Here's the z. And we're looking for the probability that z is less than z1. z1 is 0.067. We're looking for this area here. And thankfully that can just be read off the table. So the long left tail, i.e. we're looking for the long left tail of 0.67. So we're looking for points, the z's are on the edge, 0.6, 7. I get this number here, 0.7486. That's the answer. So the answer is 0.7486. Okay, so the next question is about finding the probability that the length is between 4.99 and 5.01. So I want you to think of this as kind of a quality question as such. So we're looking for the following area. So this is back in the X picture, the length of the pipe. Let's draw the curve. And this is 5. And we're looking at between 5.01 and 4.99. Now, we knew the standard deviation was 3 millimeters. And what you'll find is, so basically 1 standard deviation, 2/3 of the data. 2 standard deviations is like 95% of the data. And something like 99% of the data is within 3 standard deviations. But this is even bigger because 1 centimeter is 3 times 1 millimeter. That's 3 standard deviations plus another millimeter. So it's like 3.33 standard deviations. It's really quite large. So we're looking for this area in here. Okay, so what we want to do is you want to, so this will be Z1 and this will be Z2. Now by symmetry, once you find Z2, you automatically have Z1 because look, it's symmetric. But if you don't find that, put them both into that formula above. I'm just going to put in Z2. So Z2 is equal to, so the X value is 5.01 minus the mean is 5 divided by the standard deviation is 0.003. And I know this is going to be plus 3.33. And therefore by symmetry or by putting 4.99 into that, Z1 is equal to minus 3.33. Okay, so we're looking for the probability that Z is between minus 3.33 and plus 0.3. This answer is going to be very, very close to 100%. So, and that's like, if you can say, oh, 99.99 of the pipes are within 1 centimeter of 5, then you're getting, oh, that's good, and you get some kind of a quality approval on it or whatever. So let's draw our Z picture. The peak, remember, is at 0, so Z. I think I'm going to do something, okay. I'm going to do something slightly different with this one. I'm going to describe something. I ran out of time in the last one. So 3.33. And minus 3.33. And sure, we may as well shade it green because it's the same as this one by our fundamental calculation. Okay, so I'm going to do this in one way, and then I'm going to describe another way of doing it. So the easiest thing to do is draw a picture of, so you should be able to draw, like this is a long left tail of 0.67, this is a short left tail of minus 1.5. You should be able to draw those if you can't understand what's going on here. But what I'm looking for is the long left tail of 3.33. So that's the area from there down. Minus, maybe I'll draw this one. So minus this little bit here. So I'll just draw this. So what we're going to do is we're going to use symmetry to say that, so this is the short left tail of minus 3.33. By symmetry, this is equal to the short right tail of plus 3.33. Now we may as well find the long left tail of 3.33 at this stage. So if we have a z value here of 3.33, what is the area to the left of it? Go down to 3.3, up there, it's barely there. 3.3 here and across. I get 9.9996. Okay, that's this one. And then this short left tail is the same as the short right tail. Oh, sorry, that should be minus. The short right tail of 3.33. And how do you find one of these ones? Well, this is equal to 0.9996 minus this area. You do the total area minus the long left tail minus this bit. So this here is a long left tail of 3.33. So this little bit on the right is the whole area, which is 1, take away the long left tail, which we've just found. So this is 0.9996 minus 1 minus 0.9996, which I think is going to be something like 0.9992, basically 99.9%. So that's a kind of a high quality. 99.9% of the data is between plus or minus 3.33 standard deviations. In other words, between within 1 centimeter of the claimed mean, something like this. Now there is another option here which I'll just describe very, very quickly. Alternatively, because this is symmetric, now it won't always be symmetric, so that's why I usually do it a long left tail take away a short left tail. But you can kind of break this up into two of these. See this? Because these are the same by symmetry because it's plus minus. So you could also do twice, and the area in here is the long left tail of 3.33 take away all this, and of course if the total area is 1, that's a half, and you'll see you'll get the same answer. This is just an alternative if you've got a symmetry going on there. So let's look at it. 2 multiplied by the long left tail of 3.33 is 0.9996. Take away 0.5, we get the same answer, 0.99992. Okay. So we'll just look at some, I haven't actually thought about your assignment yet, so it's probably good for me to show you some kind of examples here. I might be using something like this for your assignments. So assuming a normal distribution, suppose that the mean annual snowfall in a Norwegian town is 31 inches with a standard deviation of 11 inches. How many inches of snow should a structure be able to withstand? Because of course, as the snow piles up, it gets heavier. Should a structure be able to withstand using the following rules? It should be able to withstand 1 in 100 years snowfall, or 1 in 100 years snowfall times 1.5. And this here is E call it a factor of safety, or safety factor. I'm going to call it a factor of ignorance. And what it's about is, it's ignorance about maybe it's not really normally distributed. And here we'll see really how powerful this factor of ignorance is in making your structure safe. Now, the only problem is you might make your structure way too strong, but obviously there's a balance between strength and safety. Between safety and cost. I mean, you can, there's look, that's for your engineers to talk about. So first of all, here we're going to say the snowfall distribution, the snow in a given, is it a year? Yeah, annual in a year, is normally distributed with a mean of 31 and a standard deviation of 11. So the snowfall distribution looks something like this. So your peak here is at 31. And you're seeing about 2/3 of the data within 1 standard deviation, which is 11 inches. So between 42 and 20. So 2/3 of the time this is where the snowfall is. Now what we're interested in finding here is the 1 in 100 year snowfall. So we're trying to find the amount of snow that happens once every 100 years. So we're trying to find the amount of snow that you get 1% chance of more snow than that. Okay, so in this case, we want to find an A such the probability that X is bigger than A is, where am I getting 1 in 200? Did it say 200? Sorry about this confusion now. Oh, it's 200 the whole time, sorry. So 1 in 200 is 0.5%. Okay, so we want to find this A value. So what we do as usual is we transform it to a problem about Z, and you want to find from the Z tables like 0.5% in here. So you're talking about 99.5% in the long left tail of A. So we're going into our tables and we're trying to find 99.5. So it'll be in this 9950. So let's have a look. 9950. So you got a choice here between these two. So I think, so this is an example of one where you probably, it doesn't really matter which one you pick, but I'm going to argue that I think we should pick this one. Because like you want to play it conservatively. So now it's it's no real difference really, but just in terms of your thinking, like should you pick this one or this one? What we're going to be calculating is an amount of snowfall that is the average, which is 31, plus a certain number of standard deviations, a certain number times 11. And what we want to do is we want to be able to withstand more snow. So we pick the slightly bigger one, which corresponds to 2.58. So here we see it. Find from the tables. Now this really says that we've got the long left tail. Let's write it here. So the long left tail of, what was the number, 2.58 is equal to 0.9951. Basically, okay. So we use this formula, which is also in the sorry, it's in your notes. So the corresponding value is the mean, 31 inches, plus this many standard deviations, 59.38. Let's call it 60 inches. So if you make it capable of withstanding 60 inches of snow, it should be good for every 200 years. But the problem is this assumption that that it's actually normally distributed is a very dangerous one. Maybe it's not, and so that's why you include your factor of ignorance. So what we're going to do here is instead we look at 1 in every 100 years and we find 56.63. But if you multiply this by 1.5, you get 85 inches of snowfall. And in fact, you can show this is, I don't think you can even show it in this. You have to use, you need a table that goes further. This is actually 1 in 200,000 years. Now, that's assuming that the snowfall is normally distributed. So this is like a black swan. A black swan is something that is assumed basically not to happen, but it can. Okay. Yeah. So I think that's everything I wanted to say there. Yeah. So if you take the 1 in 200 years snowfall, it's 60 inches. If you take 1 in 100 years and multiply by 1.5, you get far safer. But of course, there's going to be an associated cost. I'll give you an interesting anecdote, because that's the end of this lecture, about, maybe I'll give some help for these. Not. There was a similar problem posed to students a couple of years ago. So it was basically about, again, snowfall and roofs and that. And what happened was, what happened? Oh yeah, so they'd come up with a trigger that if there's this much snow on the roof, someone has to go up and clear it. You know, you see people shoveling snow off the roof. And I think one group of students got full marks because they were the only one who took into account the person going up onto the roof is an additional loading. Now, of course, the 1.5 should really cover it, but I think they were told to ignore the factor of safety and do the calculation, and they forgot about the 80 or 90 or 100 kgs of the person going up on the roof. And these are why all these factors of ignorance are in play. Yeah. Okay, so that's normal distribution.